Okay, now we'll talk about mappings, which is a combinatorial structure that is related to many of the things that we studied, and it really is an appropriate topic on which to close. It's kind of a poster child for analytic combinatorics. So what is a mapping? A mapping is an n-word of length n. So that is, we've got n characters, and every one of the characters can be anything from 1 to n. So obviously there's n to the n different n-words of length n, or mappings. That seems simple enough, but actually there's lots of interesting structure hidden under this. Because the idea is that every mapping corresponds to a digraph. So that is, you have, for every position in the word, you make a node. So there's 37 positions in this word. We have 37 nodes. And for every node, you just draw an arrow from the node to its value. Since there's n different possible values, there's n different possible places to point. So every node has out degree 1. There's only one place every node can point to. That's its position in the mapping. So 30 points to 18, 29 points to 23, and so forth. But some nodes could be pointed to a lot. That's like 33 is pointed to by 4, 14, 19, and 28. That appears 4 times in the mapping. So the sequence of numbers kind of masks this interesting combinatorial structure. And so once you see this structure, then there's all kinds of, it breaks up into things that are kind of like trees. Well, they are trees that eventually go to a cycle. So it's a cycle of trees, but there's independent components too. So natural questions that come up is, well, what's the probability the thing is connected? Or if it's not connected, what's the average number of connected components? Or how many of the nodes are on cycles and how many of them are on trees? All these types of questions turn out to be of great interest for important applications. But just as a mathematical curiosity, it's quite a fascinating structure to get out of a simple idea like an n-word, a function from a set of integers onto itself. So in order to address those kinds of questions, we'll start with something simpler called Cayley trees. So a Cayley tree is labeled, rooted, unordered tree. So labeled means all the nodes are labeled. Rooted means that there's one distinguished root. And unordered means we don't consider the order, if there's 2 children of a root, we don't consider the order of the 2 children to be significant. So there's 9 different Cayley trees of 3 nodes. So these 6 are all different because of the labels, and these 3 are all different because of the labels. 1, 2, or 3 could be at the root, but it doesn't matter what order the subtrees of the root are. Those are called Cayley trees. Now, rather than write out all the possibilities, the short form to do this is to just write the unlabeled trees and then write all the n-words that give those same trees. So for example, 1, 1, 2, so that's this first tree here. 1 points to 1, 2 points to 1, so that's 1, 1, and then 3 points to 2, and so forth. 1, 1, 1, that's 1, 2, and 3 all point to 1. So that's the n-word, and that's the tree structure that comes out of it for all those cases. So that's Cayley trees. Now the answer is the number of Cayley trees. You might have guessed that there's a power going on. It turns out to be n to the n minus 1. but that's not at all an elementary result. We're going to use a technique called Lagrange inversion eventually to get to this result that is described on the next slide. Lagrange inversion is a classic method for computing a functional inverse, and it's a very important and deep theorem. I'm not going to go into all the ramifications because we use it in quite a straightforward way. So, for example, if I have a function f of u equals z, like f of u equals u over 1 minus u, then the inverse of that is the function u equals g of z. So if I set z equal to u over 1 minus u and solve for u, I get u equals z over 1 plus z. So that's the inverse. And so Lagrange inversion is a classical method for computing this, and we'll see how it applies for us. So this is the Lagrange inversion theorem that is in our situation will be a transfer theorem to get us from a generating function to coefficients for problems where we're counting trees. So what it says is that if you have a generating function so it's g of z, and it satisfies this equation z equals f of g of z. So it's like we want to compute the inverse. When at g of z, we want to know at f. So f of 0 has to be 0 and f prime of 0 has to be non-zero. Then g of n equals 1 over n, coefficient of u to the n minus 1, u over f of u to the n, in the function u over f of u to the n. Again, we're just going to look at applications of this theorem. So just for our example, if f of u is u over 1 minus u, then g sub n, so u over 1 minus u, so u over f of u to the n, so u over f of u, the u's cancel, it's just 1 minus u to the n. So it says that g sub n equals 1 over n, coefficient of u to the n minus 1, and 1 minus u to the n. And just from the binomial theorem, that's exactly minus 1 to the n minus 1. So that says that g is sum of minus 1 to the n z to the n, which is z over 1 plus z, which is what we got from algebra. Now, you can't always get it from algebra, is the point. You have to use the Lagrange inversion theorem. So from an analytic combinatorics context, we're going to apply this as a transfer theorem, and you'll see examples of this. And we'll talk more about it in the context of the complex plane in part 2. Actually, we use a more general formulation of it, where you can, for any function h of the generating function, you can get the coefficient of z to the n in that, and it just includes an extra factor, h prime of u. H of u equals u is the basic theorem. So that's the Lagrange inversion theorem, and that's the technique that we're going to use to analyze mappings. So now let's, just before though, let's look at how it works for binary trees. So for binary trees, we have the standard construction and the OGF equation. So with Lagrange inversion, we can extract coefficients immediately from that equation because it has the form z equals a function. So if we use f of u equals u minus u squared, for Lagrange inversion. We want to find the coefficient of z to the n and t of z, and f is that minus that squared. So it's use f of u is u over u minus u squared. So we want to find u over f of u is 1 over 1 minus u. So coefficient z to the n and t of z is, according to the theorem, 1 over n, coefficient u to the n minus 1, and 1 over 1 minus u to the n. That is easily shown to be the Catalan numbers. So that's an example of the application of Lagrange inversion. So now let's look at Cayley trees. So what we want is the class of labeled, rooted, ordered trees. So in a word that just has one root, and it's labeled. And we don't, I'm sorry, unordered trees, we don't care about the orders. So with the symbolic method, we just use the construction that says a tree is a root connected to a set of trees. The order doesn't matter, so we use set. So that immediately translates to the EGF equation. These are labeled objects, so we use EGFs. It's C of z equals z e to the c of z. That's called the Cayley function. It's the one that enumerates Cayley trees. So in other words, z equals c of z over e to the c of z. So that's using Lagrange inversion with f of u equals u over e to the u. So the coefficient of z to the n and c of z by the Lagrange inversion theorem, we look at u over f of u, which is just e to the u over e to the u to the n. So it's the coefficient of u to the n minus 1 over n times the coefficient u to the n minus 1 and e to the un, which is n to the n minus 1 over n factorial. So the number of Cayley trees is n to the n minus 1, and that checks with our small values. So that's Lagrange inversion to enumerate Cayley trees. Now, that's just trees. Now we can work up to look at more complicated structures like connected components and mappings. Remember, mappings are cycles of trees. So this isn't all the mappings. These are the ones that are just a single connected component. So these are all the possible things that can happen, all the possible structures, connected structures that you can get with 3 words, with 3 mappings. So for example, we saw 1, 1, 1, so that's, or 2, 2, 2, so that's when they all point to the same thing. But you can get a structure like this where 2 of them point to each other and so forth. So these words, so 1 points to 2, say this is 1, 1 points to 2, 2 points to 1, or this would be 1. 1 points to 2, 2 points to 1, and 3 points to 1. That corresponds to that word. So these are all the ways to label and get that structure. And those are connected, so how many different ways are there to get cycles of Cayley trees? That's what a connected component is. And that turns out to be n to the n times square root of pi over 2n. And the analysis of that is, again, straightforward using the symbolic method and Lagrange inversion. So this is a typical cycle of trees, and clearly the construction we're going to use is components, a cycle of trees. And then from the symbolic method, just log of 1 over 1 minus. And that is immediately available for Lagrange inversion. Again, we've got f of u equals u over e to the u, and now our function is, because that's what the Cayley function does, and then our extra function in the Berman form is h of u is log of 1 over 1 minus u. So that's going to immediately give that, so h prime of u is 1 over 1 minus u. And then we still have the e to the un, that's u over f of u to the n. So our number of connected components is 1 over n coefficient u to the n minus 1 in that formula. And so just doing the convolution, it's n to the k minus 1 over k factorial. And change n to n minus k. And our coefficient is n factorial times that, and that's our familiar Ramanujan function, which leads to that enumeration result. So that's the number of connected components in mappings, or the probability that component is connected is divide that by n to the n, square root of pi over square root of 2n. Connected components in mappings comes directly from symbolic method coupled with Lagrange inversion. And then mappings. How many mappings are there? So that's going to cover all possibilities. And again, what's a mapping? A mapping is a set of cycles of Cayley trees. So it's going to be e to the log of 1 over 1 minus cz, which is just 1 over 1 minus cz. And that one we can get with the extended Lagrangian version with our h function equals 1 over 1 minus u. If you do the math, h prime of u is 1 over 1 minus u squared, so it's coefficient of u to the n minus 1 over n, and 1 over 1 minus u squared e to the un. You do that convolution, and this time the sums collapse. Just works out n minus k from 1 over 1 minus u squared and to k minus 1 over k factorial from the e to the un, and then we just get two sums, and they all cancel except for the last term, n to the n over n factorial. So the number of mappings is n to the n, as we expected from the trivial argument. So sure, there's a trivial argument that tells us the number of mappings, but this analysis gives the entire structure that we can use for analyzing all sorts of properties. And we'll go into the details later on. Just for example, an interesting property of these functions is something called a row length. So the row length of a function, so if we start at a given point, and just apply the function, say you have a function like x squared plus 1 mod 99. So 3 goes to 10. 10, 100 plus 1, 101 mod 99 is 2. And that, square that and go to 1, that's 5, and so forth. You eventually get to a point where you hit a cycle. So that's called the row length, the number of times that you iterate the function until it finally repeats. So in a mapping, wherever you start, you're always going to wind up in a cycle. So there's a row length associated with each point in the mapping. And this is a mapping where we have a formula to tell us what it is, but random mapping, you still have the same thing. Well, one thing to think about is what about an algorithm to compute the row length? It's kind of a fun problem. You could say, well, I'll just use a symbol table. I'll keep track of all the values I've computed, and then that way I'll know when I get a repeated value. But in practice, you can't do that because we talk about in real applications, we're doing this for huge numbers like 100-digit numbers, and there's no way you can have enough memory to keep all the possible values. So what do? Well, there's a famous method due to Floyd, which is a tortoise and hare algorithm, where you keep two variables, one that iterates the function just once and the other one that iterates it twice. So for example, so A and B start at the same place at time t equals 0, and we iterate A by 1 and B by 2. So then iterate A by 1 and B by 2. So B is going to go around the cycle, and eventually they catch up. It's not difficult to see that eventually they're always going to catch up. And when they do, actually the row length of starting at that point is between t and 2t, if t is the number of times that you had to go to get them to match. So that's an interesting, and that doesn't use any extra memory. It's just comparing those two variables. So that's computing the row length. So with mappings, again, starting at every point, you've got a row length. And that's a parameter that's interesting to study. And there's other, like tail length, that is how long until you hit the cycle. And again, number of components, number of trees, and so forth. Now, using the same method of construction and using bivariate exponential generating functions, it turns out that, I'll just give an example. So like number of components is, mapping is a set of cycles of trees, but we mark the cycles, and that'll tell us the number of components. That's one for each cycle. So immediately we get the EGF equation, 1 over 1 minus CZ to the U. And then we can work with that equation to answer questions like what's the average number of components. Or if you're doing number of trees, then it's a set of cycles of trees, and then you just mark the trees, and you get this other function. So, and we'll talk about this analysis in more detail in part 2, but for now I just want to motivate the study of mappings, and it works out to be actually without that much work that we can get all these properties of mapping. So for example, the expected row length in a random mapping is about square root of pi n over 2. And so why is all this relevant? Well, here's an actual application where it matters. This is a famous method for factoring an integer, a huge integer. And so what it's called Pollard's method, and what it does is iterates a random quadratic function to find a cycle. So it's pretty much like the function that I just talked about. We take f of x equals x squared plus c until finding a cycle, and we do it like with Floyd's algorithm, where we take two variables and iterate it once for one of the variables and iterate it twice for the other. And we use a random value of c and a random starting point, and keep going until this particular condition is satisfied, having to do with the GCD. And when it's done, you get a factor out. It's quite an amazing algorithm. So this is just an example that is doing the same thing as Floyd's algorithm done. And when the GCD of these things is not 1, then you found a factor. So, you know, why does it work? Well, it's actually not too difficult to see how it works if you know number theory, although it's definitely magic if you don't. That's not really the point of why I want to bring it up now. The question is, how many iterations does Pollard's algorithm take? And, well, one thing that seems reasonable to do is to assume that this function is not a random mapping, but since you're taking a random c and a random starting point, maybe it's got the same kind of characteristics as a random mapping. And it's conjectured, actually, that the random quadratic function of this type is asymptotically equivalent to a random mapping. And in a random mapping, the row length is square root of pi n over 2. So you can factor a number, n in square root of n cycles, which is a lot faster than trying every factor. And Pollard actually used this method to factor huge integers a while ago, and it's typical of the kind of thing that people are trying to do in cryptography nowadays, is study properties of these kinds of functions. Analytic combinatorics and properties of mappings plays a role in this kind of research. So I wanted to end with a real application like that, and end with mappings. They are quite fascinating combinatorial structures.